Is the cost of space exploration really worthwhile? It's a question that crops up regularly. Could the money be better spent elsewhere? Even if it were, one space program would still have to remain in place. That's the Planetary Defense Program, to locate, identify and deflect any wayward asteroid from hitting Earth and destroying our civilization. At the last count, there were 15,000 potentially dangerous candidates close to Earth. It's now over 2 years since the Rosetta mission reached its target rendezvous, 67P. It's been an audacious mission, gaining unprecedented forensic knowledge of the comet's surface, interior structure, composition and history.
We've noticed that there is not ice on the surface. We would be able to see that. At least not large patches of ice. You don't have skating rinks on this comet. And we also see gas in the coma. We see evidence of carbon monoxide and carbon dioxide and the elements themselves of carbon and oxygen in different parts of the coma.
And we discovered that this carbon was actually a very complex material, very complex carbon, very different from the simple molecules that we would expect to find there. So we don't see amino acids or alcohol or this kind of molecules which is observed in the gas, but we see something much more complex and very rich in carbon and poor in nitrogen or hydrogen compared to these other materials.
In particular, what we have observed is that the nucleus is composed of a mixture of materials like minerals, like silicates and sulfides, which have been formed in the inner part of the solar system, close to the sun.
Because the comet is kept in a very cold environment, we don't expect it to have very high temperature phases, so it can be that this material was formed closer to the sun and was then brought to the comet later. And this for us was a surprise because we knew it for the minerals but not so much for the organics. So it seems that the organics also can be transported over large distances in the solar system.
The most prominent, the most exciting changes on the surface, I believe it is still the big drop in the Imhotep plateau, which was 3 meters and 100 meters in height and hundreds meters in radius. But we have seen smaller scale features like a boulder, which was at least 50 meters big. It was 10 tons heavy, which, well, on the comet is just a chocolate bar of 100 grams or so, but still it's a massive thing, which has moved by 140 meters, likely due to activity, but we don't know the real reason.
It was time to decide what to do with Rosetta now its mission was complete. One option was to land it on the comet.
there were discussions about what would be the priority for the end of missions. So there were several scenarios put together, and one of the options was to do those very close flyovers. And I mean, in terms of the science objectives, that was the one that will bring us the more interesting scientific results. So it was decided by the science working team to go for this scenario. So yes, that's a very first, again, another first of Rosetta.
Rosetta's trajectory was altered to spiral into the comet, taking photos as it closed in.
Rosetta's blown it all open. It's made us have to change our ideas of what comets are, where they came from, and the implications of how the solar system formed and how we got to where we are today. And we've only, like Philae, just scratched the surface. And it's important to note, Rosetta mission is both the lander and the orbiter. Together, they have made it possible to do the science, to make the breakthroughs that we have. And we have only just scratched the surface. We have decades of work to do on this data, so the spacecraft may end, but the science will continue. That's what we're here for. That's what this mission was for.
We just have had a loss of signal at the expected time. This is another outstanding performance from flight dynamics. So we'll be listening for the signal from Rosetta for another 24 hours, but we don't expect any. And so this is the end of the Rosetta mission. Thank you and goodbye.
One major problem faced by Rosetta and its Philae lander was low gravity. When the lander's harpoons failed to secure it to the comet, it tumbled and bounced until it was lost in the rugged terrain. But engineers love a challenge, and they have already come up with a novel answer for next time. It's called the Hedgehog.
So instead, together, JPL and Stanford have been working on a totally different rover concept that is well suited to these environments, called Hedgehog. Instead of rolling around on wheels, the Hedgehog design actually puts 3 flywheels on the inside of a cube. By spinning these flywheels up very slowly and then very quickly applying a brake, which transfers all the momentum from the flywheels, we're able to cause Hedgehog to either hop or tumble or perform small adjustments. So we've done many tests here on Earth in gravity offloading test beds. Recently, we have flown 2 Hedgehog prototypes on a zero-G aircraft. In these tests, we demonstrated that we would be able to perform on a comet or an asteroid. Hedgehog doesn't have a right way up. Instead, it can tumble over the surface and come to rest on any one of its faces and still work perfectly.
JAXA's sample mission from asteroid Itokawa from the last decade returned mixed results. It did, however, teach engineers and designers many lessons about the difficulties of collecting samples from asteroids. Their second attempt is currently underway. Hayabusa 2 is coasting towards another asteroid, Ryugu, and should reach its destination in the middle of next year. This new and improved robot has several new capabilities built in. They include ion engines, navigation and attitude control systems, and an explosive device to dig into the asteroid and return material from within it. Also on board are a probe and 3 miniature rovers. a secondary probe launched with Hayabusa called Procyon had an engine malfunction and will not complete its mission. NASA's attempt at an asteroid sample return is also underway. OSIRIS-REx was launched from Cape Canaveral Air Force Station's Space Launch Complex 41 and is on its way to intercept the near-Earth object Bennu.
2, 1. And liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
Bennu is a B-type asteroid of approximately 500 meters diameter. It completes an orbit around the Sun every 1.2 years, and every 6 years it comes very close to Earth. These close encounters mean there is a high probability of Bennu's impacting Earth in the late 22nd century. Bennu's size, primitive composition, and potentially hazardous orbit make it the ideal OSIRIS-REx target asteroid. It will first survey the asteroid to find an ideal touchdown site.
Understanding the shape of asteroid Bennu is going to be absolutely fundamental to understanding the geology and putting it in context. The other reason you really need to understand the topography extremely well is that when we're going in to take a sample, it's a very, very fine measurement. And so if you're coming in, you've got the sampling head at the end of this arm that has to come in perfectly square to the surface. If you don't understand shape, sort of at a 30 centimeter scale, you're not going to be able to collect a sample.
The 7-year mission will see OSIRIS-REx touch down for only a moment to retrieve a surface sample of the asteroid, then return to Earth to deposit the sample return capsule somewhere in Utah in 2023. NEOWISE has been a reliable workhorse, operating long past its planned lifetime, but its mission will eventually come to an end. Engineers estimate it will move into too much sunlight to function. However, the team is eyeing a new space telescope, one with a little more muscle. The Near-Earth Object Camera, NEOCAM, is specifically designed to hunt asteroids. The proposal has been funded for further study by NASA. Undergoing preliminary work is the asteroid impact mission, AIM, whose launch could come as soon as 2020. A joint NASA-ESA project would see ESA launch AIM to a binary asteroid, Didymos, and its satellite, Didymoon. They were discovered over 20 years ago and are part of a group of asteroids called the Apollo Group, near-Earth objects that cross Earth's orbit and are a potential threat. ESA's part of the mission is to orbit and study the asteroids, in particular their orbits around each other.
AIM will rendezvous with asteroid Deimos in June 2022. The first thing it will do is to take high-resolution images so that we can reconstruct a 3D shape of the moon. And then we will use this data to test a new optical communication system with a laser transmitting these images down to Earth in a very quick way. After we do these measurements and we have the 3D model, we will sound the interior structure of the asteroid by deploying a small microlander on its surface that will emit the small radio waves that will be captured by AIM and reconstruct the interior structure. After we have done these measurements, the spacecraft will move away about 100 kilometers from the system, waiting for DART to arrive and impact the moon.
NASA's contribution DART is a kinetic impactor traveling at 6 kilometers per second.
Once the impact has occurred, then we will look at the ejecta and the dynamics of the ejecta cloud. We'll come closer to the moon and repeat the same sets of measurements so that we can understand the changes in interior structure and the shape and the morphology of the crater before and after the impact. AIM is the first mission to test the kinetic impact deflection technique. It's the first mission that will prove deep space optical communication systems, and it's the first mission to deploy CubeSats in this space and test inter-satellite communication systems. Also will be the first mission to rendezvous with a binary asteroid and characterize it so that we can understand how these bodies are formed, which is highly linked to the way the solar system has formed.
By measuring Didymoon's physical properties and its orbit before and after DART's impact, scientists will gain valuable knowledge that can be applied to a real threat should it ever occur. NASA is proceeding with long-term goals such as a manned sample return from an asteroid. A robotic spacecraft would locate and capture a small asteroid and redirect it into a lunar orbit. An Orion capsule would then rendezvous with it. Astronauts are now training and developing techniques for such a complex mission. There are still many things to be learned about asteroids and the dangers they might pose. As this animation shows, the inner solar system is awash with asteroids. Many of them are near Earth's orbit. Some even cross our path from time to time. All these possible hazards need to be identified, their orbits must be calculated to a high degree, and their threat assessed. Finally, we need to develop the technology to mitigate any danger to our planet. There are several groups of asteroids based on where they orbit. Those within Earth's orbit are Atens and Amors, while the Apollos cross Earth orbit. The majority of asteroids reside in the main asteroid belt between Mars and Jupiter. Then there are the Trojans, trapped within Jupiter's gravitational pull. And beyond that, other remnants of the solar system's formation can be found caught in the orbit of Uranus. There is a great deal more to be learned and understood about these other asteroids. To this end, 2 new asteroid missions have been planned and funded through the development stage. They will study 2 very different types of asteroid. The first of those missions is Lucy, which will visit a target-rich environment of Jupiter's mysterious Trojan asteroids. The mission will launch in October 2021 and fly by its targets between 2025 and 2033. In all, Lucy will study 6 Trojans and 1 main belt asteroid. Trojans are fossils of planet formation, and so will supply important clues to the earliest history of the solar system. The second is Psyche. This mission will explore one of the most intriguing targets in the main asteroid belt, a giant metal asteroid known as 16 Psyche. About 3 times farther away from the Sun than the Earth is, this asteroid measures about 210 kilometers in diameter, and unlike most other asteroids, which are rocky or icy bodies, is thought to comprise mostly metallic iron and nickel, similar to Earth's core. Psyche could possibly be the exposed core of an early planet, which lost its rocky outer layers in violent collisions billions of years ago. The mission will help scientists understand how planets and other bodies separated into their various layers: cores, mantles, and crusts. Psyche will map features, structure, composition, and magnetic field, and examine a landscape unlike anything explored before.